Again, good morning, good evening, good afternoon. I thank everybody for coming to the 3D printing webinar presented by Professionally Managed Candidates with speaker David Shear. First of all, I'd like you to understand that I am short and to the point, so please understand that I'm not rushing it. It's just the way I speak, so I do thank you for understanding. Today we'll be going over some case studies that will show 3D printing can be used in the motorcycle industry. Some of the topics we will be covering are 3D printing can reduce weight, increase strength, which gives you a clear competitive advantage and increase your salesability. The Ducati case study, where Ducati reduced its build cycle by 20 months, which reduced costs, and how it can be applied into your business. How to reduce costs and overhead by using 3D printing. The keys to successful application of additive manufacturing and the possibilities it offers. How 3D printing will increase speed of manufacturing of motorcycles and increase revenues for first movers. David will speak for about 30 minutes, and then we'll have a 5 to 10 minute question section for you guys, which you can type in the chat box, and I will ask them the questions. At the end of the webinar, we will be sending out the slides and the audio so you can share it with your group. I appreciate everybody who's on the call, and I will hand it over to David now. So just give me 1 second.
Really quickly, I am a journalist. I follow the 3D printing industry, and as a journalist, of course, I have a very broad, somewhat superficial view of the industry. However, I get to see a lot of the things that happen at all levels, and the motor industry is one of the sectors where most things are happening, and there are some things happening specifically in the motorcycle industry that are interesting to look at. And so we're gonna start with a little overview, just so everybody's on the same page here. So the presentation is about the use of 3D printing in the motorcycle industry, but first we're gonna really just look a little bit at what we mean by 3D printing. We're going to use parts of a presentation by Stratasys, who is one of the biggest 3D printer manufacturers in the world, of course. And so 3D printing is known by many names. These are some of them. You know, it's also it used to be known as rapid prototyping, rapid tooling, rapid technologies, rapid manufacturing, additive fabrication, additive manufacturing, additive layer manufacturing. I mean, the bottom line here is that it's rapid and it's additive. The funny thing is that sometimes people are disappointed at the time it takes to actually manufacture one single part by 3D printing. But the bottom line is that you have to compare making a unique prototype. You have to compare the traditional process of making a unique prototype, or actually making something that doesn't exist, to the 3D printed process, which is really, you can pretty much make any part in just a few hours. So that's why it's called rapid manufacturing, rapid tooling. And so the actual definition is that 3D printing is a collection of technologies where products, where items, where objects are made directly from the CAD, from the data in the CAD files. So 3D CAD files, the data contained in the 3D CAD files is used to make a product, an object additively, so layer by layer. So you have to imagine just anything made as a collection of 2D slices, one over the other. So one slice, the machine just adds one slice onto the others following the instructions of a CAD file. So that's the broad definition of 3D printing. So what is possible today already with this technology? This is also comes from Stratasys, and these are the basic areas. So you can do conceptual modeling, so you can and functional prototyping. So you can make models of that are not going to be used inside something that actually works, but you can also start to make actual prototypes that actually work. So that you can prototype parts of a motorcycle, an entire motorcycle, and actually use it, you know, run it. And this is the prototyping part. Then there is the digital manufacturing part, and there are two. It is divided in two. One part is manufacturing tools. So say you need to have a particular tool that has a, you need to have a particular to do a particular job. You need to have a particular shape tool With 3D printing, you can just produce it. You just design it and you produce it. You don't have to have tools to make tools. It's very fast and immediate. So this is the big area, is the tooling and the manufacturing. I mean, we're starting to see now that for certain parts, for certain types of parts, certain geometries, you can actually manufacture them, the final part, using 3D printing. So let's go on to some of the benefits in the first part, in the prototyping. So the primary benefits are this, that you reduce the time to market, so the prototype is done a lot faster. You solidify the design earlier, so you get the right design much faster. You reduce late design changes because you make all your prototyping. You get to see all the errors fast in the early phase of the prototyping, so you don't have to do changes when it becomes really expensive to go back and change something. You lower the product development cost because, of course, you cut times, or you cut materials. You do this by making the design changes earlier on in the process, and you are able to make all the mistakes that you want in your prototyping phase. The secondary benefits is that you can actually communicate better with your customers. I mean, say you need to prototype a new part. I mean, you can actually show the final part to the customer even before it's produced. They can hold it, so it's totally different to hold something physical compared to seeing it on digitally. You know, just a digital design, even if it's 3D. Digital is totally different to have the actual proof of print. And this all obviously leads to improved product design. Some applications of the direct digital manufacturing, so the second part, some of the things that are already done with the final parts that are done with 3D printing. You can do short-run production, so there are some, say you only have to make 50 parts. You can do that with 3D printing, and it's a bridge tooling, so you can have tools done faster and at much lower costs, special tools. You can have much more complex parts. So for some parts, if the part is particularly complex, it becomes more convenient to do it by 3D printing, even for longer runs. So one thing that people always say is that in 3D printing is that complexity is totally free with 3D printing. And you reduce the lead time, of course. And when is it acceptable to use 3D printing? When aesthetics is not an issue, because the 3D printed part does not come out finished from the machine. What takes the longest time is actually the finishing part, creating the part and finishing it. The machine can do all the work very rapidly. So aesthetics should not be a critical aspect. Or the finishing process is feasible. So say you have a very complex part, sometimes you're not able to actually smooth it out or apply a finishing process to it because it's too intricate. So you have to consider these things. And that the physical properties, I mean, sometimes 3D printing has a broad range of materials that you can use, but you have to evaluate if the properties of those materials are acceptable for what you need to make. Some examples of final products that are made with 3D printing in the automotive industry, and that could be useful in the motorcycle industry, of course, is jigs, fixtures, check gauges, drills, alignment tools, tooling masters and patterns, and so on. The benefits for when you make end-use parts with 3D printing, okay, you have lower cost, you have shorter lead times. I mean, you can make them in-house, or you can have them delivered by a service next door at much faster times than if you had to actually have them produced abroad. The secondary benefits are you have, depending on the technology, but you have so much more design freedom. There are some technologies for which there are no geometrical limitations. There are few manufacturing constraints. You have the freedom to change your design much more often. You're able to do mass customization, which means you can make a different, say you have to make 50 parts, all different, all for one single. You can make 50 different parts in the same print. Of course, we're talking about small parts, for example. For example, 50 parts with a different name on them, just to make it a simple example. It supports lean initiatives. So say you want to start producing just a short amount of components, of parts, of products. You can do that. And you can have, of course, true just-in-time manufacturing, because you can make it, just as you need it. And of course, you reduce warehouse and space and inventory costs, because there is no space. I mean, your entire inventory can be digital, and then utility printed on demand. Moving on. Okay, so this was the premise. Now, here are some suggestions for tools that you can use to actually understand if 3D printing is right for you. One thing is so when should you use 3D printing to make something? You have one tool that is available to you is called the 3D Print Barometer by Materialise. Materialise is one of the biggest 3D print services in the world. It's a Belgian company that has over 1,000 employees worldwide. This tool is at 3dprintbarometer.com. It will you just have to input your data, and the tool will tell you if it's worth it for you to use 3D printing or not. So you input data on the part size, on the part complexity, on the project, the entire project's value, series size, and so on, and you calculate whether it's worth it for you to use 3D printing or not. How much does it cost to use 3D printing? Here is another tool that can be useful. There is a company called this is an American 3D print service, very good company. It's called C.Ideas. They're experts in 3D printing. They use most of the primary technologies, and they have an engine called the TrueQuote engine. You just upload the CAD file of your that you need to produce, and they will give you. You select the machine, you select the materials, and they will give you the exact quotation on price in real time. This is something that there are other companies that offer this tool. This is one of the most complete tools that you will find around. So here, the address here is truequote.buildparts.com. So now that we had an overview here, we're going to look at which are the main 3D printing technologies that you would use in the motorcycle industry. So the main technology, the primary technology, this is the first technology that was invented. It's called stereolithography, SLA. It uses, it's the main manufacturers of this technology are 3D Systems. Materialise, they have a machine that 3D Systems is the main patent holder. Materialise has their own version of the technology, but since it breaches 3D Systems patent, they cannot sell it. They only use it in-house to offer service. DWS is a small Italian company that does SLA machines with a different type of SLA technology. And there is a small company, American company called Formlabs, that makes a very low cost but very high quality 3D printer. I mean, this is a machine that costs $3,000, and if you consider that most SLA machines, the lowest costing ones are $20,000, but they can easily go up to over $1 million. So they use these machines. They use photopolymer resin, so there are between 50 and 100 different materials available that you can use. It basically uses a laser to solidify the laser and to solidify the photopolymer. Photopolymer is a polymer that becomes solid when light hits it. That reacts to light. In this case, it becomes solid when light hits it. And one advantage of stereolithography is that you can go from very small, very high resolution to really large objects up to 2 meters. So Materialise's technology is capable of doing 2-meter long items. Another version of stereolithography is called digital light processing. It also uses photopolymer resins. There's about 50 materials. The market leader in this field is EnvisionTEC, a company called EnvisionTEC. There's other companies that use this technology, and there is an availability of low-cost machines because the technology, the main patent has expired, and the technology is pretty easy to replicate. So there are now appearing on the market a lot of low-cost machines costing around between 1,500 and 10,000 euro. Sorry, dollar in this case. The difference in this technology is that it projects, instead of using a laser to solidify the photopolymer, it uses a digital projector. So wherever the image, the projector projects the slice onto the resin, and wherever the slice is projected, the resin becomes solid. And moving on to a different technology, this is fused deposition modeling uses a plastic that is melted, so it uses a thermopolymer. And the advantage and the main benefit here is Stratasys. There are also, this is the most open source technology. There's hundreds of low-cost 3D printer manufacturers. This is the most low-cost technology, but the prices of the high-end machines can go up to several tens and hundreds of thousands of dollars. In this case, it melts a thermoplastic to produce the layers of the object. The disadvantage is that you have several geometrical limitations because you need supports, but the advantage is that you can use end-use plastics to make objects. So you can use plastics such as ABS, nylon, and the plastic called Ultem, which is an extremely fire temperature resistant, chemical resistant, very flexible, and yet very, very strong type of plastic. And the most commonly used material is PLA, which has very low mechanical properties, but is really easy to print. So if you need to make a non-functional prototype, that's the material you want to use. Going on to another technology, this is called material jetting. This is a technology that is used also for metals, but it does require the post-processing. It basically creates the layers of the object by gluing together powder. So it glues together powder to make, and then it deposits another layer of powder, and it glues together the slice so that you get to the final object. The main materials used for this technology are mainly. Oh no. Sorry, I actually went ahead. This is material jetting. It's actually another photopolymer-based, so resin-based, liquid resin-based technology. This is offered by both Stratasys and 3D Systems with different names. So PolyJet is Stratasys, and Multijet Modeling is 3D Systems. And this is the advantage of this technology. Is that it's the only technology that lets you do multiple materials in the same print job. So you can do up to 3 materials. You can do multicolor and multi-density in the same job. So this is excellent for prototyping, not for final products. Selective laser sintering is the most industrial technology there is. This instead of gluing together the slice, it uses a powder, but it melts it. It melts the powder with a laser to make the slice. So the most commonly used material here is nylon, which can be charged with other materials such as carbon fiber or glass fiber to make it more resistant. There's about 10 materials used for this technology, but it's mostly nylon. But this technology gives you full geometrical freedom for the parts. It lets you do fast, precise, solid, end-use products with no limitations. So this is the most commonly used technology. The machines start at about 200,000, but this main patent also has expired. So there are beginning to appear lower cost systems on the market, but we're still talking around 20 to 40,000, and they're very limited at this time. This is the binder jetting technology we were talking about before with the powder that is glued together. This is technology that allows you to make really big parts. So there's a company called Voxeljet that makes huge parts using this, basically gluing together powder. In Voxeljet's case, it's sand powder, so you can make big sand casts. But you can also glue together gypsum or clay or metals. But in the case of metals, you need the post-processing, so you need to actually fire up. You need to sinter the green parts glued into an oven at very high temperatures. So it does have less size limitations than fused deposition modeling, and it is less expensive than SLS, but it does require post-processing. This is where all the growth, where all the interest of the industry is right now, is the metal-based technologies. So we're talking selective laser sintering of metal. which is similar to the plastic process but uses metal powders. SLM, which is selective laser melting, which is similar to SLS, but it actually fully melts the powder, so it's able to create fully dense parts which can be worked in using subtractive technology, so using a CNC mill or laser cutter after they've been printed. Another metal technology that is very advanced, that offers a lot of possibilities, called EBM, electron beam melting. This is done by a Swedish company called Arcam Metals, and it does offer even more production freedom. It's faster. It offers several advantages over SLM. However, most of the times you will find that no technology substitutes another technology. There are some things that should be done by one technology, and some things should be done by another, which is a good reason to turn to a service many times. You can the materials used in these technologies in metal technology are mostly titanium, steel, and cobalt chrome. They're able to produce fully dense solid metal parts with no geometrical limitations. The maximum size is about 1 meter. There's a machine called the X-Line 1000 by a company called Concept Laser that does about 1 meter parts in metal. So here we go. Now we're moving on to the case studies specific to the motorcycle industry. Once again, I'm going to give a brief overview of these. There are links here that you can go to find out more in depth, more details about all these studies. The first one we mentioned, that Al mentioned, is the Ducati, like we say in Italy. Ducati worked with Stratasys, and then we're going to see, okay, these are the ones that we're going to see. So the Ducati, this Energica Ego is an interesting project that we're going to talk about. And we're going to take this case study of a bicycle to show a process called topological optimization, and how we're going to understand how that could be applied to the motorcycle industry as well. So the Ducati, basically, what happened here is that Ducati moved the prototyping process in-house by acquiring Stratasys machines. So these are FDM machines, diffuse deposition modeling professional machines. So you can make you can make end-use parts with these. And so this is the link that you can find more information at. Excuse me. This is the engine that was prototyped by Ducati in this case study. And basically what happened is that Ducati had to reduce the time to market for the new product. So to help meet this challenge, they brought in the FDM machines, and they were able to use them to build concept models and functional prototypes from ABS, polycarbonate, and polyphenylsulfone, which are all thermoplastics. So basically, the most interesting things here are that they cut time and that they cut costs. So they cut up to 20 months from the development process of the Dismos ADG race bike. And so basically, they were able to assemble it in only 8 months with doing the prototyping in-house. Before that, it had taken 28 months. How that happened, you can view at this link. But basically, they were able to do all the prototyping on locations. So this also adds to the security. You don't have to share sometimes models, digital models that are sometimes really need to be kept as a secret. Before that, the majority of the prototypes were outsourced in Ducati. So this is a case study that shows that there are advantages to bringing the prototyping in-house with the right 3D printers, because now they're fairly easy to use. I mean, so you basically just need to have the CAD model. So real savings, they were able to cut the cost significantly. They basically what happened. What they said is that they used to spend up to $1 million a year on the prototyping activities, and for much less than that, they were able to purchase the machines, which they bought a Stratasys for this machine, which it's a line of machines. The largest one of which cost about 700,000 and can do parts that are up to 1 meter wide. But there are there are much lower costing ones. It depends what you need to do basically. So now they're able to produce higher qualities of parts at a fraction of the cost, but they're also able to forecast the cost for each project much more accurately. So this is what Piero Gius, the R&D CAD manager for Ducati Motor Holding, said. You can, once again, you can go look more in details about everything that Ducati was able to achieve by bringing the machines in-house. The next interesting case study is this Energica Ego. This is a electric motorcycle which was entirely prototyped by 3D printing by this company called CRP Group. This is a company that was born as a prototyping service, and they became specialists in SLS technology, and they started developing their own materials for SLS technology. And they also this is a small company that was able to create this entire motorcycle, which the development process began in 2013. And the motorcycle is actually on the market as of 2015. This is that you see in the photo, in the small photo, is the prototype that's almost entirely 3D printed. I mean, all the plastic parts are 3D printed, and most of the metal parts are 3D printed. So they use their own materials, which are called wind form. They have a line of materials. This is nylon charged with the carbon fiber or glass fiber or some other additives. So this is what we said, is that they developed the bike in 2 years. They created a one-to-one scale master model of the Ego, which they drove for several thousand kilometers. And these are the parts that I'm sorry, but I cannot see the entire screen. But there are, they listed the parts that they actually 3D printed, and these included the dashboard mount that acted as a support structure for the front fairing, and the mirrors, the undersaddle, the saddle, including the rubbery part, because you can actually, there are many ways to go about it, but you can 3D print a lot of flexible materials. So other 3D printed parts include several covers, cable clamps, front and rear fender, and for each part, they were able to select the right material for that part. So some parts had to be more resistant, some parts could be less resistant. They had the right material for that part, and they 3D printed it on site. The Windform family is a polyamide nylon charged with different additives. And these are some links where you can find out more information about them. And finally, we're going to move on to what is probably the most interesting possibility that 3D printing offers us, and it's the topological optimization. So this is something that is mostly done with metal 3D printing. Basically, Renishaw, which is a big UK manufacturer of industrial machines, also produces an SLM 3D printer, so selective laser melting 3D printer, which produces metal parts by fusing the powder together. And together with a company called Empire Cycles, they designed the frame of a mountain bike to take advantage of this technology. But basically what they did is they used topological optimization. So they distributed the material in those places that needed it most. So the places that needed to be stronger had a higher density of materials, and the places, the spots that didn't need as much material, the material was removed, and the designs were using generative software. They were able to geometrically design the parts so that they could remove even more material. So the end result is that the frame was 33% lighter of the original compared to the original. This is something that they did for a motorcycle frame, which, by the way, was printed as in a single print job, is what you see here in the top left corner. They 3D printed it as a single print job, all the parts of the frame, which were then assembled. So So basically, they took full advantage of the technology, both by removing as much material as possible without losing on structural integrity. So the test was to keep removing material without reducing the integrity of the part, of the frame. This, of course, using additive technology gave them the ability to do rapid iterations, more flexibility, ability to make shapes that were derived by topological optimization, which is obviously done through software. Ultimate customization and tailoring, so they could do anything. They could give any shape to the frame. Even put the name of the rider of the in it, of course. They were able to make more complex shapes, and this is something also very interesting that you can do with 3D printing. Of course, you can do hollow structures. You don't need to actually produce to do a cast and produce the two halves and then put them together. You can make the hollow structure as a one single piece, which adds to the structural integrity of the part. They were actually able to make the seat post bracket as much as 44% in their traditionally manufactured aluminum alloy version. They tested it, and the material is corrosion resistant and as long lasting as any traditionally manufactured frame. There's one last thing. Of course, one possibility for the motorcycle industry, just like for any industry, is toy making, is custom toy making. So this is an example of a designer that I know that makes that 3D prints toys, and he produced this fat boy. Of course, his idea was to actually propose to Harley to create a custom version of a custom motorcycle. So anybody could have a toy version, a miniature version of their own personal custom motorcycle, which would be extreme personalization, which is one of the possibilities available to 3D printing. Here are some other examples. So this is assembled. He designed the parts, and then you can assemble them. So this is something. Another thing that you can do is, this is an Italian company that developed a remote an RC motorcycle toy. This is also sold as a kit, as a 3D printable kit. So they sell you the designs, and then you 3D print them, and most of the parts are 3D printed, not all of them. And then you make you build your own RC motorcycle. These are just some examples. Of course, it's just the beginning. People are exploring new avenues, new ways to manufacture, more personalized, more efficient, in a more efficient and a more cost-effective way. So this is me. I'm David Scher. These are my contact information. If you need more information on this, on specific parts of this presentation, these are the websites I mostly work for. I'm based in Italy, so I actually have my own website for Italy, but the main website I write for is called 3dprintingindustry.com, which is an English language website. And that's about it. If there are any questions, I'm available.
I appreciate the information you gave us, and I do have some questions here for you. One of the questions that came up was, is there a service out there that could tell if it's more cost-effective to use it in-house or to out-house it? I was wondering if you knew any services like that.
I'm sorry, can you say that again?
Is there an ROI model that you can use to see if the printing would be better to do outside, or if it's more cost-effective to bring it inside?
Yeah, I guess, it's really something to consider on a case-by-case basis. What we are seeing, and what the Ducati case study, which, by the way, it's from a couple of years ago, so from about a year ago, so that showed that it was much more, that it becomes more convenient to bring the prototyping in-house. However, the bottom line here is that the solution is usually a combination of both. So what we're seeing is that more and more companies are starting to do pre-prototyping in-house. So you buy a low-cost 3D printer or an average cost 3D printer, and you do the pre-prototyping phase in-house, and then you do the final prototyping phase with the materials, the specific materials, specific high-end technology that you need. You can outsource that. But you do the pre-prototyping phase in-house, which speeds up the entire cycle. So it depends what your size is, what your needs are. It really depends on that. But in general, anybody can bring the pre-prototyping phase in-house, because most 3D printers now start at only a couple of $1,000s. So
okay,
it would be a combination of both, I guess.
okay. Someone asked, do you know anything about honeycomb titanium 3D printing?
I guess, yeah, that's a little too specific for me, but I'm guessing the honeycomb structure. I know I follow a lot of the medical aspects, and in medical they use trabecular geometry. Trabecular titanium, and I'm guessing with the honeycomb is similar. I mean, it's a way to reduce material and it's a way to create products by generative software. So what we're seeing in 3D printing software is a huge part. It's true that 3D printing is making things physical, but the software is the biggest, is a huge part. So what's happening now is that CAD software is really becoming computer-aided software. Like it was never before. It never really made things easier. Now it's starting to make things easier because we're starting to see generative software, where you set up the generative parametric software, where you set up parameters and the software makes the part for you. And the honeycomb structure is a repetitive pattern that the software can use, I think, to optimize the mechanical and physical properties of that part. Unfortunately, I cannot go more in detail on that because I'm just a journalist.
I understand. Another question was, would you think it'd be possible to replace fiberglass with a cheaper material through 3D printing?
I honestly, I don't know that either, but what I can say is that more and more we're seeing different blends of materials. So sometimes you don't need, with 3D printing you can use a resin and just have a lower percentage of fiberglass and yet obtain almost the same properties. So that becomes a lot less expensive as a material. It's just a matter of blending. We see that with many different materials.
Okay. Another question was, does 3D printing have the same mechanical properties as traditional manufacturing parts?
Yeah, that's a good question because it depends on the technology that you use. With the resins, all resin-based technologies, the problem with resins, you can get really resistant, hard, fire-resistant, chemical-resistant resins, but they tend to lose those properties rapidly or over time. So they tend to deteriorate over time. With the FDM, you get the same exact, ABS is ABS. The strongest plastic that you can currently 3D print is Ultem, which 3D prints at about 400 degrees, not 400 but almost. So you cannot make, like for example, they're not able to 3D print with PEEK yet, but the materials they use have the same, almost the same exact properties of the traditionally manufactured parts. Maybe not exactly the same, especially with ABS, but with metals, yes. I mean, with the selective laser melting and electron beam melting, you can have the same exact properties of the traditionally manufactured parts in metals such as titanium, steel, Maranging steel, and so on. Iron also. But what was I going to say? I'm not sure because I hear a lot of different versions, but from what I understand, with ABM you can actually have superior properties as you can have parts that are even more dense than the traditionally manufactured parts.
Okay, and just one more question for you, David. How do I determine which technology is right for my needs?
That's the most complex part because there are about 30 different technologies and about 500 different machines on the market. So finding out which one is the best one for your needs is probably the hardest part. I mean, because no technology replaces any other technology. So you really need to speak to somebody who is an expert in this. But for the prototyping, especially for the pre-prototyping part, really the lowest cost one would be the best one, I guess.
All right. I appreciate it, David. That was a great presentation, and I thank you. I just have a little bit more to do here, and I thank you for your time, sir.
Thank you very much. If you need anything, you have my contact information.
Sounds good. Well, I thank everybody for showing up to this webinar. I don't know why you showed up today, but it could be because you wanted to be on the leading edge of technology. And I'm hoping today that you took away that 3D printing can decrease the production time and increase your profits dramatically, that your competitors are starting to use 3D printing such as Ducati and Harley-Davidson and more, and that you need to take the next step in 3D printing in your production needs. Which brings me to the question, how do I do that? Well, I think there's two ways. One, you can do it the slow way. You can do it yourself, which means you need to learn a whole new field. You need to go through a ton of resumes to find people. You're going to spend a lot of time away from what you're doing, what you should be doing, and you're going to fall behind your competitors. Or you could do it the fast way. You could hire experts. We already have the experts in our candidate pool. We've placed over 300 experts in the motorcycle industry, and we want to be your partner in this process. And this may sound bad to some people, but we have fired clients before just because they're not working with us. This has to be a partnership. We have to work together to be able to grow your business. So that's why I think using experts in your field would be the best mode. So you can do this yourself and fall behind the industry, or you can hire experts. If you want to hire experts, just click on this link here and we can set up an appointment and discuss things. I do have a couple of questions that came in for me, so I just want to go through them and then we'll finish this up. Bill wants to know if the sales call is going to be this call is going to be a sales pitch. No, it's not. This is a fact-finding call. We're just going to find out what your needs are, see if we can work with each other and see if we work together. So it's not going to be a sales call. We're not going to try to sell you anything. We're just going to talk and see if this is a fit for you guys or not. Some people have asked for the link, so I am going to send the link to you. I'll send it through chat. And then Steve here I see is asking, why should we use us other than other recruiting companies? And I could tell you all the things you've heard from other recruiting companies. You know, we've been in business for this long, we've done this, we've done that. But I'd rather just tell you a short story of what I think is why you should use us. One of our largest clients decided to bring us in as a recruiting company on a probational trial. After 6 months, they fired all their recruiting companies and only used us solely, and they've been doing that for the last 2 years. So I'm hoping that will be something that at least gets you on the call and talk to us a little bit. I appreciate your time. I thank you for coming to our webinar, and I look forward to speaking to you guys one-on-one and hopefully see you on our next webinar. Thank you and have a great day.